Hey everyone, this is the Space Channel. Since the dawn of time, humanity has endowed the sun with divinity. The fear and worship of it were actually quite justified. After all, what else but the sun made life on this planet possible? Its astonishing and mysterious influence on us has become clearer thanks to centuries of research, modeling, and observation. So today, especially for our dear sun, we're going to look at 10 fascinating and lesser-known facts about it. I'm sure some of them will surprise you. Let's dive into it together. The sun rotates in a very strange way. The sun's unusual rotation around its axis was noticed as soon as astronomers began observing sunspots. It turned out that the sun's layers near the equator rotate faster, while those closer to the poles move more slowly. For example, near the equator, the sun makes a full rotation around its axis in about 24 Earth days, whereas near the poles, it takes around 34 days. That's a big difference. This kind of movement is known as differential rotation, and it's standard among astronomical objects made mostly of gas or liquid. Even gas giants like Jupiter and Saturn exhibit this type of rotation. Of course, this effect doesn't occur in the rocky planets of our solar system, since they are solid bodies, unlike the sun, which is made of hot, gaseous plasma. Anyone patient enough can actually observe differential rotation themselves. By carefully tracking the movement of sunspots over several months, you can even calculate the rotation periods of different solar layers and create a similar rotation chart. Alternatively, you can use images of the sun taken at different times, which are freely available in the SOHO spacecraft's database, for example. If this really sparks your curiosity, you can even conduct your own mini-lab experiment on the topic. Here's an educational guide from the European Space Agency's CESAR program, which aims to engage students in astronomy. Pretty fascinating. In summer, the sun is actually farther from the Earth than in winter. Some of you might have thought it was the other way around. It's hotter and sunnier in the summer, so the sun must be closer to the Earth, and colder in the winter, meaning it's farther away. But in reality, the seasons on Earth form for entirely different reasons. It all happens because of the tilt of Earth's rotational axis relative to its orbital plane. This tilt is 23.44 degrees. By the way, that's another fascinating fact we mentioned in one of our earlier videos. The tilt is not constant. It slowly changes due to a phenomenon called axial nutation, with a complete cycle lasting about 41,000 years. But that's a topic for another time. It has been known since Kepler's time that Earth's orbit is an ellipse, with the Sun at one of its foci. The point in Earth's orbit that's closest to the Sun is called perihelion, and our planet passes through it between January 2nd and January 5th. The point farthest from the Sun is called aphelion, which Earth reaches between July 3rd and July 7th. According to Kepler's second law, which states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time, the Earth moves more slowly near aphelion than it does near perihelion. This means that Earth's orbital speed changes from about 29.29 kilometers per second to 30.29 kilometers per second as it travels along its orbit. And once again, you can verify this yourself. Here are my photos taken near perihelion and aphelion. Unfortunately, I wasn't able to photograph the Sun precisely during those intervals. But even so, the apparent angular size of the Sun in the images is noticeably different. The Sun is actually green. Sunlight appears perfectly white, that's obvious to everyone. Back in his day, Isaac Newton passed sunlight through a prism and obtained a full spectrum of colors. The solar spectrum, in fact, is very similar to the spectrum of what physicists call a black body. So what is a black body, and how is the Sun similar to one? A black body is a theoretical model of a physical object that completely absorbs and emits all electromagnetic radiation, meaning radiation of all wavelengths. It's usually represented as a box or a sphere with a small opening. Inside, the walls of this object are made perfectly black so they can absorb all incoming radiation. Once a black body reaches a specific temperature, it begins to emit thermal radiation, and its spectrum depends only on that temperature. This spectrum is precisely described by Planck's law of radiation, and the Sun is one of the best real-world examples of an almost perfect black-body radiator. The spectrum of the Sun is almost identical to that of a black body with a temperature of about 6,000 Kelvin, nearly identical. Today, we know that the Sun's radiation spectrum also contains absorption lines, known as Fraunhofer lines. These are dark regions in the spectrum that indicate radiation of specific wavelengths being absorbed by something, for example, atoms of hydrogen, calcium, or iron. Because of this, the Sun cannot be considered a perfect blackbody, but the blackbody model can still be effectively used to study the solar spectrum. From there, we can easily determine, using Wien's displacement law, a relatively simple formula, the wavelength at which the Sun's radiation reaches its maximum intensity. When you plug in the numbers, you get 502 nanometers, which corresponds to green light. Could that be the reason why most plants are green? Let me know what you think in the comments. Of course, our Sun emits radiation across a wide range of wavelengths, but its peak emission falls in the green part of the spectrum. The atmosphere is hotter than the surface. Inside the Sun, thermonuclear reactions occur at temperatures of about 15 million Kelvin. As we move outward toward the so-called surface, the temperature gradually drops to around 6,000 Kelvin in the photosphere, the visible layer of the Sun. However, in the higher layers of the solar atmosphere, the temperature rises again, reaching up to 100,000 Kelvin, and in the outermost layer, the solar corona, the temperature can soar to about 1 million Kelvin. Why does this happen? Let's start from the inside. The photons and other particles produced by nuclear fusion travel through nearly 2/3 of the Sun's radius, carrying heat that warms the lower layers of plasma. These hot layers rise, while the cooler upper layers sink, a process known as convection. Essentially, it's a kind of mixing motion. But this mixing of plasma also creates powerful magnetic fields, which in turn give rise to sunspots, prominences, loops, spicules, and other solar structures. These magnetic activities are responsible for heating the Sun's atmosphere to much higher temperatures. The streams of plasma generated by turbulent magnetic fields during these convective movements can produce magnetohydrodynamic Alfvén waves, oscillations that propagate through the plasma at high speeds. These Alfvén waves rush into the solar corona, where they release their energy, heating it to extremely high temperatures. This process is only one of many hypotheses that might explain the extremely high temperature of the solar corona, since scientists still don't fully understand all the details. However, for now, this explanation is likely and is supported by data from the Parker Solar Probe, which we'll discuss later in this video. The Sun will not die. The evolution of stars has been studied in great detail, and even a school student can use the Hertzsprung-Russell diagram to show what will happen to a star like the Sun over the next few billion years. It's known that the Sun has already used up about half of the hydrogen fuel needed for thermonuclear fusion. This means it will remain on the main sequence for a few more billion years. Over time, the temperature will continue to rise, while the amount of available fuel will steadily decrease. In about 5 billion years, the Sun will begin to enter the red giant phase. Its outer layers will start to expand, while the core will contract. Nuclear fusion involving hydrogen will no longer occur in the core itself, but instead in the layers above it. Eventually, the core will contract so much that the intense temperature and pressure will ignite helium fusion reactions. This will trigger a helium flash, releasing an enormous amount of energy. As a result, the star will temporarily stabilize. It will even shrink slightly for a short time. But once all the helium in the core is burned out, the star will begin to expand again. The fusion reactions will move to the outer layers, and the solar wind will start blowing away the Sun's outer material. Through this process, the star will lose a significant portion of its mass, while the core, now fully contracted and no longer capable of sustaining nuclear fusion, will remain behind as a white dwarf. The white dwarf phase, often thought of as the Sun's final and fatal stage, is actually the longest-lasting one. It's not the complete end of the star's life. The planetary nebula, formed from the star's outer layers, may persist for tens of thousands of years, but the white dwarf itself will continue to exist for many trillions of years. Over time, it will cool and emit less radiation. After about a quadrillion years, it will slowly transform into a black dwarf, an object so cold and faint that it no longer emits any visible light. That is, of course, if the universe still exists by then. So our star will not die anytime soon. It will endure for as long as the universe itself. Parker Solar Probe. When talking about facts about the Sun, it would be a sin not to mention the very mission that made most of this knowledge possible. The Parker Solar Probe was created for that exact purpose. The Parker Solar Probe is a NASA spacecraft launched in August 2018 to study the Sun's outer atmosphere and the solar wind up close. Its main objectives are to explore the Sun's corona and uncover the actual cause of its extremely high temperatures, to study the flow of charged particles that erupt from the Sun's surface during solar flares and coronal mass ejections, and more broadly, to investigate the mechanisms of solar activity itself. You might be wondering, how can Parker get so close to such a hot star? One of its key protective features is a heat shield over 2 meters in diameter. Thanks to this shield, the spacecraft's instruments can continue to operate stably at temperatures close to room temperature, even as the sun-facing side endures intense heat. Here's a fact about Parker that will probably amaze you. The probe is set to approach the Sun at a record-breaking distance of just about 6 million kilometers, or 3.7 million miles, and it will do so with the help of Venus. Surprisingly, the gravitational pull of Venus can be used to perform such gravity assist maneuvers. Through this method, the probe gradually loses orbital energy, allowing it to move into a closer orbit around the Sun. Even more astonishingly, during these maneuvers, it will reach an incredible speed of about 700,000 kilometers per hour, or around 430,000 miles per hour, making it the fastest human-made object in history. A total of 7 such maneuvers were planned, 6 of which have already been successfully completed, and Parker is now approaching its long-awaited goal, the Sun itself. The Sun is not 4.5 billion years old. Here's a short, and maybe a bit amusing, fact for you. The Sun is actually about 20 years old, 20 galactic years old. We know that the Earth rotates on its axis in nearly 24 hours, and at the same time orbits the Sun in about 365 days, what we call one Earth year. But the Sun itself, along with all the planets, asteroids, comets, and other cosmic bodies bound by its gravity, is orbiting around the center of our galaxy, the Milky Way, where a supermassive black hole resides. According to scientific research, the solar system takes roughly 225 to 250 million Earth years to complete one full orbit around the galactic center. So if we assume the Sun is approximately 4.6 billion years old, a bit of simple math shows it has completed around 20 such orbits around that black hole, which means, in galactic terms, our Sun is only about 20 years old. Photons from the Sun's core never reach its surface. The photons produced by thermonuclear reactions in the core of our star exist under extreme conditions. Temperatures around 15 million degrees, incredibly high density, and a sea of ionized gas. All of this prevents newly formed gamma rays from reaching the Sun's surface directly. If it weren't for these conditions, a photon could reach the surface in just about 2 seconds. But instead, it takes them hundreds of thousands, or even millions of years to make that journey. In the process, each gamma photon undergoes multiple transformations. It gradually loses energy and eventually emerges as a visible light photon. Here's how it happens. Right after being produced, a gamma photon travels only a microscopic distance before it's absorbed by another atom. That atom then re-emits another gamma photon as a result of recombination, and this cycle repeats countless times. So, in essence, no gamma photon escapes directly from the sun's core. Instead, photons are continuously absorbed and re-emitted, slowly making their way outward over immense timescales. Only in the outer layers of the sun, where the density and temperature are much lower, can photons move more freely. By that point, after countless interactions, they finally escape from the sun's surface, not as gamma rays, but as visible sunlight that reaches Earth. The sun is losing mass. By now, most of you probably trust Einstein's theory of relativity, and if not, I encourage you to check out a few of our videos on the subject. The famous equation always works and everywhere, demonstrating the fundamental physical relationship between energy and mass. Our sun releases an enormous amount of energy every single second. Therefore, according to this formula, it must be losing a significant amount of mass. And if we also add the solar wind, the continuous stream of charged particles, that loss becomes even greater. Let's do the math together. We'll start by expressing the mass in terms of Einstein's equation. E stands for energy, and c stands for the speed of light. If we replace E with the energy emitted per unit time, that is, the sun's luminosity, measured in watts or joules per second, then m will represent the mass lost, measured in kilograms per second. The speed of light in a vacuum is about 300,000 kilometers per second. Now we have everything we need for the calculation. When we substitute the values, we get an astonishing result. The sun loses about 4.25 billion kilograms every second. That's more than 367 billion tons per day. Sounds alarming. It might seem like the sun is burning itself out very quickly, but actually not at all. Compared to the sun's total mass, this loss is minuscule and has no significant impact on its long-term evolution, even when we include the solar wind's contribution. To put your mind at ease, here's one more fact. Throughout its lifetime, the sun has lost only about 0.5% of its total mass through radiation. Sunset. To wrap things up, I encourage you to go outside and watch the sunset today. It's an incredible sight. No matter where you are, it always looks beautiful. But here's something that might surprise you. When you're watching the sun set below the horizon, you're not actually seeing the real sunset. Think about when you stir tea with a spoon. You notice how the light bends where it passes through the surface of the water. Something similar happens to the light from the sun, the moon, and other celestial objects as it passes through Earth's atmosphere. Our thick atmosphere acts like a variable lens. Directly overhead, at the zenith, light refraction is minimal. But near the horizon, you have to apply a correction to the apparent height of celestial objects, sometimes as large as 35 arcminutes, or more than half a degree. That means the farther an object is from the zenith, the higher it appears in the sky than it actually is. This phenomenon, called atmospheric refraction, is something astronomers must always take into account. It also creates some truly fascinating visual effects. Since the apparent diameter of the sun is about half a degree, and the refraction correction near the horizon can reach 35 arcminutes, it follows that when you see the lower edge of the sun's disk touching the horizon, the sun is actually already below it. We're just seeing it thanks to refraction. In other words, if Earth had no atmosphere, you would see the sun already set at that moment. The same goes for sunrise. When we see the sun appear above the horizon, it's still below the horizon. The moon and other celestial bodies are affected in exactly the same way. In addition, the atmosphere slightly distorts and flattens the sun and moon near the horizon, making them appear wider and oval-shaped at their poles. So, Not everything is quite as it seems at first glance. That's all for now. If you enjoyed the video, don't forget to like and subscribe to the channel. Enjoy the sun while it still shines. And see you next time.